Okay, so last time, this was kind of what we finished off with. A denumerable union of denumerable sets is denumerable. This was a step up from the union of two denumerable sets is denumerable, which is crazy enough, right? But even a denumerable union of these is. If you notice, I said, well, think about this as an exercise. I'm going to use this result, but not prove it until we get to the next section. And you'll see why later. This is a fact that we will show later, depending on something else. And the last thing we proved is any subset of a countable set. And remember, countable means either denumerable or finite is countable. Corollary. 536. A subset, a set, is countable. Well, again, remember that means it's either denumerable or it's finite, if and only if it's equivalent to a subset of the matching numbers. It can be put into one-to-one correspondence matching numbers. And I will leave that one also as an exercise. Let me, I want to state this theorem here. I'm not going to prove this. It will follow for some later things. It's not difficult to prove. Let me just kind of talk you through it a little bit. And then we're going to do some technical stuff for a little while. If A and B are countable, and so is the union. Okay, case one, A and B are both finite. Then the union is finite and countable, right? A is finite, B is denumerable. Well, now you have a finite set union a denumerable set. That's denumerable and hence countable. The fact it's denumerable goes by induction on the fact that we know that if you take a denumerable set and add another element to it, union another element to it, then it's still denumerable. And the last case is if A and B are both denumerable, then that follows from what we will prove later. So you notice in some of these results, it's almost frustrating, I think, a little bit, because we reduce a lot of these to the sets being disjoint. And we say, well, okay, if these sets are disjoint and you union them, they're denumerable. And that might seem a little bit frustrating, right? Because if they have overlap, it seems they'd be smaller, so still denumerable, right? But technically, the disjoint helps us get through things. So here is kind of a garden variety way of taking care of this. What if your sets happen to have overlap? So let's let AK be a numerable collection of numerable sets. So you've got this large, countably infinite collection of, oh, actually, at this point, I don't even need sets to be denumerable for this level, right? Because this doesn't have any. much to do with counting. Now, for each k in the natural numbers, let bk be ak take away uh, um, then uh, bk is a numerable collection of sets such that the union of bk is the same as the union of the a-pairs. Yes.
You subtract the unit sets with the sets.
What did I say? No, I do mean the union. Okay, by the way, can anybody tell me, I'm gonna make one more statement, it's not done here. Anybody know? Can anybody kind of describe what BK does? Well, BK is sort of AK, right? But what do? You subtract all the A's that were before it. And the BKs are pairwise disjoint. Right? Let me point out that B1 and A1 are the same thing, right? Because there's nothing to take away at that point. All right. What's B2? It's A2, take away all the stuff that was already in A1, so the stuff you've already done. What's B3? What's A3, take away the stuff in B1, A1 and A2. So you're jerking out the stuff that you've already seen. So there's no repetition here. That's the point. This makes a disjoint family. So let's go through why my statements here are valid. Proof. Certainly is a numerable collection. Let me point out, this is just by definition, because BK is defined for every K. Let me point out something here, that what happens if A1, A2, A3 forever and ever are all the same set? Then B1 is A1. What's B2 then? If all these sets are the same, B1 and A1 are the same. B2 is A2 take away A1, but A1 and A2 are the same. So what would B2 be?
No set.
All right, and B3 would be A3 take away A1 and A2, it's the same thing. So this is a denumerable collection, but some of them could be empty, right? But it's still, I mean, I feel like a total idiot writing an infinite number of empty sets, but it certainly is a denumerable collection. So let me point out, notice that each BK is contained in AK. I think we could all agree with this because BK is AK with perhaps some stuff missing. So this means that the union of the BKs is contained in the union of the AKs. That's not too much of a problem. For the other containment, suppose A is in the union of AK. Suppose you can find something here. I need to show it lives in one of these. Well, A is in this union. So what does it mean for A to live in this union? It's got to live in one of the states. So for some M in the natural numbers, A is in A sub M, right? Now here's my trick. Let M in the natural numbers be smallest, such that A is in M. Once again, you got to dig the natural numbers, right? It's that this is a non-empty subset of the natural numbers. It has to have the smallest element. So basically, A sub M is the first set that has the appearance of A in it. Notice that since A is not in a K or K less than M, then A is not in the union J equals 1 to M minus 1 of AJ. Okay. It doesn't appear in any of these smaller sets, so it's not the union. Therefore, A is in AM minus the union. And this is the. So A is in DM, which is in the union. BK. So we have the other container. So we have equality. That's this state right here. And finally, I claim that BKs are pairwise. Let's suppose A is not equal, well, M is not equal to N, and X is in I'm going to get a contradiction from this. Since these natural numbers are not equal, one of them smaller. Agree? So X is in B N M. And X is in the union if it's in BM, it's in the union of all the BKs up to M, right? But BN is AN minus, well, right. And since so X is in the union, minus. With such a pairwise. Now, what's the point of this lemma? What this lemma says is the following. If I have a denumerable collection of sets, I can change this section, I can change this. So the upshot is this. If AK is a denumerable collection of sets, then BK is a collection with number one, I've got this refined collection, and two, the utility of this is as follows. If I want to prove that, say, a collection of sets that their union is countable or denumerable or something like this, I can assume, this allows me to assume that the collection is pairwise disjoint. Because what this lemma does is it takes my collection of sets that might be messy, sloppy, overlapping, and replace them with a collection of sets that have the same union but are pairwise disjoint. All right. And the pairwise disjoint, oftentimes when you're proving things, it's easier to do things that way. So this is a useful lemma. It's going to allow us to right. So we're going to get to this here. We know that I've given you the theorem that a denumerable union of denumerable sets is denumerable, and we are going to I'm going to formally prove this. I give a sketch of the proof in the notes in theorem 5.3.9. I'm going to skip that till we get to the action of choice and get back to something that is more concrete. But let me give you a corollary to this business about denumerability. And this is a big one. You will see this, I'm quite sure, in advanced calculus / real analysis. If you take those, whichever one you take, or and other places too. And this was a big theorem. countable union of countable sets. It's countable. This is a big theorem. It's very, very useful. The heavy lifting is done by the theorem that says a denumerable union of denumerable sets is denumerable. And like I said, I'm going to give you actually a formal proof of that later. We need to develop just a little bit more to get formal proof here. But notice countable allows you can replace each countable with the word denumerable, and it's correct. Countable allows the option of a finite collection of finite sets or a denumerable collection of finite sets, some of them finite, some of them denumerable. So this is just a little bit more flexible. But like I said, the heavy lifting, the big shocker is the fact that a denumerable union of denumerable sets is denumerable, and everything less than that is certainly countable, right? So this is a mess on aisle 5. We'll clean up later. Okay. Cardinal numbers. We had this result that used Cantor's diagonalization that showed that 0, 1, the interval from 0 to 1 is in a certain sense strictly bigger than the natural numbers. What we proved is there's no bijection from the natural numbers into the interval from 0 to 1. We showed, in fact, there's a 1-to-1 function from the natural numbers to 0 to 1. But no matter how much you wiggle around, you can't make that function cover all of it. You can't make any function cover all of the numbers between 0 and 1 on the real line. This seems really strange, but that's the way infinite sets work, strangely, right? For example, that's an infinite set, right? I can pull half of it out and make 2 sets, the evens and the odds, and they're still both infinite sets, right? And in fact, they're of the same size. You could also throw in all the half integers, right? 1.5, 2.5, 3.5, and so forth. It's the same size. It's one giant Hilbert hotel. The thing about the interval from 0 to 1 is there's not enough room and there's not enough hotels to take care of that in the following sense. Anything that is the smallest infinity that's denumerable, that means you can list it, right? The rational numbers, if you're careful enough, you can list it. The first rational number, the second, the third, fourth. It won't be in the same order as you see on the real line, but you can rearrange the rationals and list them. You can list the integers. You can list the rational numbers. You can list the n cross n. You can list n cross n 1,000,000 times, right? You can all put those in an ordered list, right? There's too many to ever list. And that's why sometimes higher infinities are called uncountable, right? Because you can't put them in a list. No matter how you try to rearrange the numbers from 0 to 1 and put them in a list, you will fail. You can't do it. It can't be done. And in fact, it's worse than that, because now you've got the real numbers, or let's just say the interval from 0 to 1, that's a larger infinity. You could use that for your list, but there's a bigger infinity where that one doesn't list with regard to the real numbers, and it just keeps going. And I'll give you a theorem that shows that. Yes.
Is the interval from like 0 to 2 that a larger infinity than the interval from 0 to 1?
No. And that's part of the problem of, you remember the homework problem where you have to have the bijection from the interval AB to the interval CD? That shows that no matter what the length of the interval is, they're all the same size. They're bigger than the naturals, but those are all the same size. And in fact, the entire real line is the same size as the interval from 0 to 1, for example. But the set of functions on the interval from 0 to 1 to the reals, that's bigger. There's more functions than there are numbers between 0 and 1. Yeah, it gets worse. Let's just embrace the madness, shall we? So let's start off with kind of a nice little result here that this is really a definition, so I'm repeating myself a little bit, but it's not gonna injure any of us, right? Definition. Let A and B be sets. We say that the cardinality of A is equal to the cardinality of B if there exists a bijection F matrix. Okay, no surprise there. We say A is less than or equal to B if, anybody remember what this is? Good. There's one, so there's a one-to-one function in that direction. Alternatively, there's another way to think about it, and we'll get to this later, is there's an onto function in the other direction. 3. We say that A is strictly less than B. Yeah, there exists F from A to B that is 1-to-1, but no bijection. Or in particular, no onto function. Right. So we say that the cardinality of A is less than B if, yes, you can find a one function that gives you less than or equal, but no matter how you try, you can't find an onto function, or there's no bijection. And that's equivalent to saying there's no onto function. And you can also formulate that in the other direction as well. Okay, so let me give you a theorem here. Let A, B, and C be sets. A, B, and C be sets. Number 1. Number 2. Um, well, I get this problem. Sorry. Oh, A is less than B If and only if. Oh, oops. Brothers, name, listen, name. If and only if. Uh, a subset of B implies six. A. Cardinality of A is less than or equal to cardinality of T. If and only if there exists a subset of B such that okay, so let's go through some of this at least. Okay, for one, I'm actually going to prove something stronger. I can just want to show you how to do it. Okay. Can anybody think of a bijection from A to A? Right. This is just the identity function, takes every element A to itself. This is a bijection, so in particular, it's one to one, right? So A equals A, and it is one to one. So A plus A. So in fact, the particular one-to-one function that we use is also a bijection. So you get the stronger statement that A is equal, the cardinality of A is equal to one. Okay. Two. Means there exists F from A to B that is one to one. And B, C means there exists G from B to C such that G is one to one. Now, what do we need to do? We need to show that there's a one-to-one function from A to C. Any ideas? F and G are one to one. Any ideas how to find a one-to-one function from A to C? Yes. So yes. Proposition. See, don't tell me your homework problems aren't useful because we have to show that in homework, right? That the composition of one-to-one functions is one-to-one. So number three, this is called Jim's patent sloppy. Replace the one-to-one with bijection. And it's the exact same proof that we have here, right? Because that homework said we also showed that the composition of two projections is bijection, right? Number 4, this one is A, B, means there is this one-to-one function F from A to B. If a bijection exists, then, and if not, by the definition that I gave you in class, that holds, because this means that there exists a one-to-one function, no bijection, and either one exists or it doesn't. Right? And the other way is there exists a one-to-one F from A to B. In this case, you can find a one-to-one map from A to B that is also onto, but even if you have this case, you still got the one-to-one map. Number 5. This one I think is, I mean, you would hope that this part of the theorem is true because this says, hey, if you've got a subset of another set, then the size of the subset should be less than or the size of the parent set. This is what reasonable people would hope would happen, I think. The interesting thing about infinite sets is this is what sets infinite sets apart from finite sets. This subset in the infinite case can be proper and they can still be equality. Right? If you have a proper subset of a finite set, if you got a set of 9 things and you throw out some of them, then that subset's going to be smaller, right? But if you take the natural numbers and throw out 1, or even throw out all the odds, it's still the same size. And that's why infinite sets are a bit hard to work with. Let's prove this. Consider the inclusion map from A to B given by IA equals A. This is sort of just like the identity map. The only reason it's not the identity map is because the codomain might be bigger, right? Just take any input here and just send it to itself, which is an element of A, which is contained in B. So this is, in fact, an element of B, right? No. Right. IA equals IA prime means A equals A prime. There you go. The last one. For this direction here, suppose F from A to B is 1, 1. That's what it means for the cardinality of A to B by centering cardinality of B. X be. Let me remind you what this is. So, let X be the image. This is, if you will, this is the range of F. It's a subset of B. No. F from A to X is a bijection. Right? Because I already know that F is 1-to-1. And by definition, every element of X is in the image of it. So I kind of cheated here, right? What I'm saying is this function is 1-to-1. It might not cover all of B, but it covers all of what it covers, right? And what it covers is a subset of B. And so notice that because of the fact this is a bijection, and there's your subset of B, of course, this works. Now suppose there exists X and B such that so there exists a bijection F from A into X subset of B. Right. And now let G inclusion happen. That is to say G of X equals X. F is 1-to-1. And so it's G, because it's like sort of a baby apple in that. So if you do F and G, this goes from A into B. And is 1-to-1. So cardinality of A. And that proves theorem of Cantor. Now I am going to prove for you an astounding theorem. And we're going to finish here with this theorem today, because tomorrow I'm going to prove the Cantor Schrader-Bernstein theorem, and that might take all of class to go through. It's a tough theorem, and so we're going to take some time to get through this. The Cantor's theorem is at least as astounding as this, and the proof is shorter. I might talk a bit more about this. Let A be any set then cardinality of A is strictly less than the cardinality of the power set. This, I think, should astound you. I hope it does. This is not surprising for finite sets. We know this, right? Because if a set's finite, say it's got n elements, how many elements does power set have? I remember. It has 2 to the n, right? We have n elements in the original set, 2 to the n in the power set, and 2 to the n is always bigger than n. You can use calculus to grab a function. But this is saying something. If you have any set, even an infinite set, then the size of the set is strictly smaller than the size of the power set. So I give you an infinite set, you say, I'm gonna look at this power set. You've got, if this set is infinite, the power set's infinite and bigger. Now take that set, look at its power set. It's infinite and bigger than that. And you can do this forever. In fact, it's out of control how much you can do this. First of all, let's prove this very astounding theorem that gives the existence of an infinite number of sizes of infinite sets. Proof. Consider F from A into the power set of A, given by F of A is just the set A. This is 1-to-1. And so the cardinality of the set is less than or equal to the cardinality of this power set. No surprises there. We now show there doesn't exist an onto function from A to B. And so if there's no onto function, you can never have a bijection. It's impossible. This is actually an amazing little trick here. Suppose there exists G from A to the power set of A, such that G is onto. So suppose that we can find some function G that maps from A to the power set that is onto. Now I am going to build a certain set in the power set as follows. Let's let X so I'm going to build a subset of A as follows. I'm going to let X consist of everything in A such that X is not in G of X. Now let's think of what this means here. What does this mean? Notice this function here. This function here takes A and corresponding to A is a subset of A, right? So take your X, and this is a subset. So what am I looking at? I'm looking at everything in A such that when I do this function to X, X is not in the set, right? So it's not in its own set. Everybody okay with that? Input X, and this gives some other set, and it happens to not contain the element X. Now I claim this set cannot possibly be in the domain. Suppose there's an A and A, such as G and A text. I mean, after all, if G is onto, this thing must exist. There must be some A that goes to X. But note, if A is in X, then A is not in G of A, which is X. Right? Everybody agree with me? If A is an X, then by definition, A is not a G of A, but G of A was X. Okay, then. So I guess it must be the case that A is not an X. Well, what does that mean? If A is not an X, then A is not in if A is not an X, then A is, yeah. Right. But if A is not an X, then by definition, A is in G of A, which is equal to X. Either way, you get a contradiction. So there is no onto G from A power Z. So there's no bijection. Because if you assume there's bijection, all you have to do is construct this subset where it's impossible to be in the image. This is a powerful, powerful theorem, because it shows even for infinite sets, there are bigger infinity. Look at this proof, make sure you understand it. Got any questions, let me know. Any questions for now? All right, well, I will see you all Wednesday. Oh, and I will say, we've got a visitor coming in from Spelman College. She's the professor and chair of the department there. She's going to talk about integer choice games. And in fact, she brought up in her abstract, that she's going to talk about rock, paper, scissors. So this might be a fun one. So I'd encourage y'all to be there on Friday.